Hello everyone, and welcome back to another GIS lecture video. And in this lecture video, I want to continue our discussion on remote sensing by talking about our second topic, this idea of electromagnetic radiation. Let's go ahead and give ourselves a little bit of room here. And let's talk about this idea of electromagnetic radiation. Okay? So, I want to start our story off with the sun. Right? Or, pretty much you could think of the sun as you could use a light bulb here, but the idea is we have something that produces light. And so what happens is that chemical processes inside of the sun produce energy. Right? And that energy is in the form of what we call electromagnetic radiation. Or ER. Okay. Now, hopefully this isn't your first time hearing about electromagnetic radiation, but if it is, just to kind of recap what this concept of electromagnetic radiation is it's the idea that anything with a temperature above absolute zero has electrons moving around atoms. And these electrons change state, right? Chemical reactions produce energy, causing electrons to change states. And what happens is, in all of those chemical processes, right, energy is released in the form of waves, right? This wave is electromagnetic radiation, right? It's energy that is propagating in a direction, moving as a wave. And so this wave has two characteristic features, right? It has this distance from one peak. Let's do that in a different color. Right? It has this distance from one peak to the next peak. Right? This is called the wavelength. So this is called the peak. Right? This dip here is called a trough. Right? So the distance from one peak to the next peak is called wavelength, and this is going to be very important. Right? So much so that I'm actually going to make a note of it. Right? Wavelength, right, is the distance from one peak to the next peak. This is going to be a very important definition for the entire rest of this module as well as the next, because this wavelength is one of the fundamental measurements of remote sensing. Make this actually a different color here so we emphasize, right? This concept of wavelength, right? This is fundamental to remote sensing. right? And we'll see why in the next couple of videos. So the first thing that we have is this idea of wavelength. Right. The next key piece that we have for electromagnetic radiation in the confines of remote sensing is the idea that if we were to stand in a fixed position, right? Let's say we stood in a fixed position here, right? And we counted the number of peaks that passed by this fixed point in a given amount of time, that's called the frequency. Frequency. Frequency is the number of peaks that pass a fixed, see if I can improve my handwriting just a little bit there, that pass a fixed point in a fixed time. Okay, so frequency is the number of peaks that pass by a fixed point in a fixed amount of time. Okay, so let's think about units, right? So wavelength, right, the distance from one peak to the next peak, right, that's a measure of distance. So we need a unit that measures distance. Well, if we think of the metric system, right, the unit for measuring distance is the meter, right? But we don't measure, right, this distance is really, really, really short. Right, so we can't measure it in meters, right? We can't even measure it in millimeters or centimeters. I mean, it's something way shorter than that. So what we end up measuring wavelength in typically is the nanometer. You'll often see it abbreviated NM for nanometer. And just for reference, right, 1 meter, right, is equal to 1 times 10 to the 9th nanometers, which if we expand out that scientific notation, right, 1 times 10 to the 9 is a billion, right? That's 1 with 3, 6, 9 zeros, right? So we're talking on the order of a billionth, right, of a meter. So very, very short distances. So next we have this idea of frequency, right? The number of peaks that pass by a fixed point in a fixed time. Well, the units here are usually given in terms of cycles per second, right? That would make sense, right? A peak passing a point would be a cycle over a fixed period of time measured in seconds, right? Cycles per second. Sometimes you'll also see this referred to as a hertz. Right? So we have wavelength, the distance from one peak to the next, and we have frequency, the number of peaks that pass by a fixed point in a given period of time. We have one more piece of information about electromagnetic radiation, and that is its speed. Its speed. Right? And so because we're dealing with electromagnetic radiation, which is a form of energy that is produced by the sun, right? Electromagnetic radiation is also sometimes referred to as light, right? So we know for a fact that electromagnetic radiation moves at a constant speed. Right? And we know this constant speed. We often refer to it with a lowercase c. Right? This constant speed is the speed of light. Right? Speed of light. And just in case you're curious, right, we know the speed of light, right? It is approximately equal to 3 times 10 to the 8 meters per second, right? Expanding out that scientific notation, right, that's 3, 1, 2, 3, 4, 5, 6, 7, 8 zeros meters per second, right? So that's 300 million meters per second. It's pretty fast. Right? So these are three things that we know about a given piece of electromagnetic radiation. We know its wavelength, measured in nanometers. We know its frequency, measured in cycles per second or hertz. And then because all electromagnetic radiation obeys this constant speed, we know its speed as the speed of light. Okay? And that allows us to do something, which is we can relate this idea of wavelength to frequency, right? We can relate this idea of wavelength, right, the distance from one peak to the next, to this idea of the number of peaks that pass by a point in a fixed period of time. So I want us to think about this for a second, just conceptually, right? So if we know that this wave is moving at the same speed, regardless of what wavelength it has, right? And we know that frequency is the number of peaks that pass by a fixed period of time, right? If we decrease the length between the peaks, right? If our wavelength gets shorter, what is going to happen to our frequency if the wave is moving at the same speed, right? As our wavelength decreases, right? By default, that means the waves are going to be it means the peaks are going to be closer together, right? That's what shrinking the wavelength means. The peaks will be closer together. And so if it's moving at the same speed, as we decrease the distance between the peaks, right, more peaks are going to pass by that fixed point in the same period of time, right? And so what we can do, let me try and give us just a little bit more space here. We'll move over just a little bit. Right, what we can do is we can relate these two things together. So if we refer to frequency as f, with a lowercase f like that, and we refer to wavelength with this symbol lambda, right, lambda, this is going to be an important symbol. Frequency we're not going to deal with as much, but so lowercase f. And we have this speed as c, right, the constant that we use across all of math and physics for the speed of light. Right, what we can do is we know the speed has to be the same, right? That is a constant, so c can never change, right? So we know that we get that speed by multiplying, right, the wavelength times the frequency, right? But as we just said, right, if we shorten the wavelength, or if we make the distance between the peaks smaller, right, we know that that's going to increase, right, the number of cycles in a given second. So what does that look like mathematically, right? If we rearrange this equation to solve for frequency, right, right, if we isolate frequency, we would divide both sides by wavelength, right? c over lambda, right? So what this equation is telling us, right, mathematically speaking, right, anytime you have a number on the denominator, right, because this is now a fraction, right, anytime the denominator of a fraction gets smaller, the overall number gets bigger, right? So mathematically, this is telling us, right, as the wavelength gets smaller, the frequency gets bigger. Visually, right, the wavelength gets smaller, the peaks get closer together. Naturally, right, that means that if you measure a fixed point for a fixed period of time, if the peaks are closer together, right, more of them are going to pass by this fixed point. So this relationship should make sense. And we can do the exact same thing solving for wavelength, right? Wavelength, which is going to be this lambda, kind of looks like an h, right, is going to be equal to c over f. Right. So what do these two relationships mean? Right? These two relationships mean, right, if wavelength gets smaller, frequency gets bigger, right? More cycles are passing in a given second. Right? If frequency gets smaller, right, fewer cycles are passing in a given second. That must mean the wavelength is longer, right? There's more space between the peaks. Right? What does that mean? Well, that means that wavelength and frequency wavelength and frequency are inverse. Right? Wavelength and frequency must be inverses of each other for these two equations to make sense. Okay? So again, recapping everything, right? We have this idea of energy being emitted from the sun at a particular wavelength and frequency related to each other through the speed of light, and wavelength and frequency are inverses of each other. In the next video, we're going to come back to this idea of wavelength and talk about how we can use wavelength to characterize the radiation that's being emitted and the role that that's going to play in remote sensing more broadly. So hopefully this all makes sense, and as always, if you have any questions, please reach out. Thank you.